Hey, Ron. So let's jump right in. So brief introduction about myself. So as Pavan said, I am a principal data engineer at DemandBase currently. I have about 8 years of experience in data engineering. And I got my start back in 2016 after graduating from Case Western Reserve University in Cleveland, Ohio. So let's start first with some background on the problem that DemandBase was looking to solve. So the idea was that we have DemandBase's primary application is a SaaS-based application backed by an OLAP database as well as an RDBMS, specifically Postgres, that stores a variety of our data. It stores application configuration data. It stores our customer data from integrations and other sources. All variety of data, and then that data is then transferred to the OLAP database for analytic queries from our application. Our RDBMS Postgres, as I said specifically, is organized into more than 25 different RDS instances. And then within each instance, it's organized into a schema per tenant format. So schema per tenant is this concept of having a single database schema per customer with the exact same set of tables across all of those schemas. So the idea is that you have a strong separation of customer data at the database level such that it is kind of fully logically separated. And then to get the data from from its source in RDBMS as well as other internal data sources, we have a Spark-based ETL that runs to do a variety of different analytical calculations, calculating different metrics, and whatnot from that RDBMS data as well as other upstream data sources that we have internally. So the question then kind of becomes, how do we use that RDBMS data for our analytics? The data there is extremely valuable. We have tons of teams internally that want access to that data, whether that be data science, other analytics teams internally for general reporting based on the data there, based on customer configuration, etc. However, accessing the data where it lives is very, very difficult. Our application makes direct calls to the database through our API. So the performance of our application, to some extent, is equivalent to the performance of our RDBMS. So when we're trying to get data out, especially in bulk for analytical purposes, we need to be very, very careful about how much load we're putting on our Postgres databases. In addition to that, broad data access can be very difficult for our analytics use cases or data science use cases because we have this schema per tenant set up in Postgres. So when you're thinking about how do I view or how do I do data analysis or data investigation across all of our customers to build a new model, you would have to go and access albeit the same schema table, say like an account table that has the same schema, there are 1,000 of those tables that exist because there's one per customer. And additionally, kind of last thing is combining data in our RDBMS with other data sources that we have internally becomes very difficult. How do you combine data that lives in Postgres with data that's in BigQuery, data that is in Parquet files in S3, etc.? So the question became when we set out on this was, how are we going to get this data out of Postgres efficiently and effectively? So there were kind of three main options that we looked at. So what if we push all of our data into our RDBMS and scale for both use cases, scale for our application use case as well as our analytics use case? This solves the problem of being able to use data from a variety of sources because we're pushing that data to live in the same place. However, scaling to that level becomes very, very costly very quickly. You're essentially, doubling or even tripling your database costs at that point. And then it really doesn't solve the issue of schema per tenant access. You still have these multiple iterations of a table that you need to access across. The other one that we looked at was pulling data out of the Postgres instance in bulk. And putting it in, someplace. Maybe it would be Parquet files on S3. This works well now because you're able to take the data out and have it in kind of a more centralized format. And wherever you put it, you can make sure that it's scalable and performant, etc. However, doing this kind of bulk access out of the database, especially via something like Spark, can be quite slow, and it can be really intensive on the database itself. And as we said before, because the performance of our application is more or less equivalent to the performance of our database, this would have a direct impact on our customers, a direct impact on our application performance, and that's something we want to avoid at all costs. So the route that we ended up going was, how do we stream the minimal set of changes out of Postgres such that we can then recreate the data downstream in a stable, scalable, cost-effective format? So this is where the idea of change data capture came to our rescue. So this gives us the ability to only take the exact amount of data that we need out of the database at any given time to then recreate those changes in another data store to have a consistent copy of that data somewhere else. Additionally, this has no effect on the performance of the database because we're not actually querying the data out, because we're connecting to the internal replication. It doesn't have a real effect on the performance, so we don't have a performance decrease on our application side. So let's talk a little bit about the basics of change data capture. So most relational databases today, Postgres, MySQL, etc., have the ability to replicate data internal to the database to a read replica. So in Postgres in particular, this is done by using what's called the write-ahead log. So the idea is that when a change happens in the Postgres database, information about that change is written as a message to the write-ahead log. To do replication internally, a replica then subscribes to what's called a replication slot, and via that replication slot, they are able to receive these write-ahead log messages, and the replica will then apply them internally so that there's a consistent copy in a Postgres read replica, say. So these WAL messages give you kind of all of the information that you need to recreate the data on some replica, whether that be an internal read replica or some other replica. It gives you information about the before state of the row, the after state. It gives you a variety of metadata about the transaction that the change was included in, the schema, the table. It also includes what's called a log sequence number, which is a monotonically increasing identifier of where that change happened inside of the write-ahead log. So you have essentially all of the information you need in these messages to fully recreate that data in a read replica, say in another Postgres instance. However, the idea kind of becomes, if this is how Postgres does its internal replication, if this is its chosen manner of doing replication because it's efficient, because it's effective, because you can guarantee ordering, etc., why don't we do the same thing? We're trying to create a replica somewhere else outside of Postgres. Why don't we use this mechanism as well to create our own replica in a different data store? So to do this, we're using an open source tool called Debezium. Like a read replica, Debezium is able to subscribe to the internal replication process of the RDBMS. So in this case, the write-ahead log of Postgres. So rather than applying the changes to a Postgres instance itself, like a read replica would, it streams those changes then into Kafka. So what we're then able to do is we now have a persistent ordered queue of changes that we can use to recreate this replica of data. So we have all the information we need now in a persistent place to then recreate this as a replica. But how are we going to do that reconciliation of data? We have basically these change messages which represent inserts, updates, and deletes, as well as some others like truncate messages. How are we actually going to, in a straightforward and relatively performant manner, reconcile those changes into the final data set? How are we going to apply them? So this is where SQL's merge into syntax comes into play. So the high level of merge into is that there's really kind of these two very general cases. There's this concept of being matched and being not matched. So in merge into, you have a target table, which is your downstream table that you're applying the changes to, and you have a source table, which is your set of changes or the data that's incoming. So when we say that a row is matched, it means that the row in the source exists in the target. And when it's not matched, obviously the row in the source does not exist in the target. So these two kind of cases become when the row is matched, so when it exists in the source and the target, and the operation of that change is a delete, then you delete the row in the target. Otherwise, you update the row. And then when the row is not matched, therefore it exists in the source and does not exist in the target, and the operation is not a delete, you need to insert that row. Otherwise, it's a no-op, because if the row is not in the target and you're trying to delete the row is already deleted. There's nothing to be done at that point. So by doing this, we're really able to then apply all of our changes downstream into whatever system we're using to run this merge into syntax. However, one of the problems that we ran into relatively quickly is that the basic cases of merge into are relatively straightforward, as I just laid out, but there are very quickly many nuances when you try to do this in production. And there's one in particular that I wanted to talk about because it was one that was particularly difficult and kind of particularly interesting. So in these basic cases, one of the major assumptions that's being made is that on every message, we have all of the information we need to recreate that data downstream, because in general, that is the case. However, there are cases where that's not exactly true. So particularly in Postgres has these concept of toast values. So toast values are very large string and binary values that under the hood, Postgres doesn't store with the rest of the data. Under the hood, Postgres actually will store this as a separate internal table that has these toast values. And these toast values can be very, very large. They can be hundreds of kilobytes or even megabytes. So what Postgres does internally when it's doing replication to keep replication efficient is that if a row has a toast value in one of its in a column, and that value has not changed, Postgres doesn't send you the value of that column. It will just send you a placeholder that says unchanged, essentially. So now you're in a situation where in all of your rows, you don't necessarily have all of the information that you need to recreate the row. So your merge cases start to expand in kind of permutations. So there was two things that we had to do to deal with this. First was we had to collapse updates for the same row together such that we could try to get the full value of the row. So say that you have a table that has 3 columns that can have toast values in them. In a given batch of changes, you could have multiple changes for that row, where in some of the changes, data is present for some of those toast columns and not others. And you can have changes where data is present for none of those columns. So from all of those changes, you can't just pick, last one wins, because you don't have all of the information for all of those columns. You have to collapse those rows to try to get, or not to try, to get the most updated value for all of those toast columns. However, even in that case, maybe there is a column or two that haven't had any changes in a given batch. So you still have these placeholder values. So in that case, you need to, what we essentially need to do is generate many more of these merge cases that handle the fact that a row can have an unchanged toast value and not update that value in the downstream table because we would essentially be updating it with just a placeholder value. So the basic cases when you're talking about CDC merge into are relatively straightforward, but there's a lot of nuance very, very quickly as you get into kind of real world cases and real world scenarios, especially with cases like toast values in Postgres. So at this point, we have an architecture that looks like this. We have our databases. We have n number of them at DemandBase. I think right now it's 29. We have a Debezium instance per database that subscribes to a replication slot on that database. And then we are able to stream those changes from those databases into Kafka topics per table. So we are now able to have a logical view of a table for all of our customers, such that we can then recreate that data downstream and have more cohesive, centralized views of that information. So then, at this point, we have our set of changes. Now, where are we going to store that data? How are we going to reconcile that data back into a consistent format? And how are we going to do that in a scalable, performant, and cost-effective manner? So many OLAP databases today support SQL merge into syntax. Snowflake supports it, as well as many others. And they scale very well. However, they can become quite costly to run relatively quickly. As well, recreating this data in kind of a plain column or format like Parquet or something else scales well. However, and it is very cost effective, of course, but it doesn't support SQL merge into. You would have to rewrite all of that logic yourself inside of your job to do that reconciliation of data, to find the data that is in the source, to match it together, and to do this yourself such that you are on the other side, you get a consistent recreation of your data. So this is where Iceberg comes in for us, because it really represents the best of both worlds. So what are the features that we get with Iceberg? And I'm sure you all have heard about these many times today through a number of sessions, as well as through your own research and stuff. But I think it's worth mentioning here as well. One of the biggest things for us about Iceberg was that it gives us cost-effective and scalable storage. At the end of the day, these are files on S3. S3 can scale nearly infinitely, so our storage is able to scale as we need it to. And because it's S3, because it's files on blob storage, the storage is very cost effective. It's much, much less than you would pay for storage in something like Snowflake or BigQuery or wherever else. Additionally, because of the metadata of Iceberg and the additional pruning and query performance that gives, you get very performant querying, both for merge into as well as for analytical queries. As well, you get a number of different features and functionality that basically make Iceberg look like a database to most of your consumers. You can read and write data simultaneously. You can do time travel and rollback, so you can roll back to different snapshots, as well as just go and query those snapshots to get data at specific periods of time. There's comprehensive schema evolution, where you can add columns, drop columns. You can partition your data. You can do partition evolution over time and change the way your data is partitioned as you go. And then, because you don't just use a storage format like Iceberg in isolation, Iceberg has a huge ecosystem of tools that you can use to then access your data and utilize it. So you get really, like I said, this best of both worlds, where you have very cost-effective and performant storage, and you're able to query that in a performant way using really, almost any tool that you prefer, because there's such large support out there, now, and there's even more support coming in other tools as well, that you get this huge ecosystem of support. So then let's bring it all together and look at kind of the final architecture of where we're at now. So data lands in our RDBMS from a variety of sources, like I said, whether that be application configuration data, customer data from integrations, etc. We utilize change data capture via Debezium to get just the minimal set of changes that we need to recreate that data out of our RDBMS. Using Debezium, we're able to stream those changes into Kafka, and have a persistent ordered queue of those changes that we can then action on. Then using Iceberg and the merge into syntax, we're able to relatively easily reconcile those changes into our Iceberg tables to get a scalable, performant, and cost-effective storage layer. Iceberg gives us all of those great features, and as well, as I said earlier, unlocks a huge number of options for how we utilize our tables now. So then, looking at the final architecture, this is what we have. So as we showed earlier, we have all of our databases on the left. We're streaming out just our minimal set of change data capture changes from our write-ahead log into Debezium. Debezium is streaming those changes into Kafka topics per table. And then we are able to run our Spark, what we call CDC ingester jobs, which take those changes off of Kafka and generate a SQL merge into a statement, as well as do some other ETL, like I said earlier, like collapsing rows, to then reconcile that data into our Iceberg tables. So the way that we organize our tables now is we have a table per what I guess I would call logical table. So say we have an account table. There is one singular Iceberg account table rather than having an account table per tenant like we do in Postgres. But then so that we still have separation of our customer data as well as performant querying when we're querying just a single customer's data, we partition our Iceberg tables by tenant ID. So all of our tenants' data is then physically and logically separated inside of those Iceberg tables. And because a lot of our queries are for a specific tenant, we're able to very quickly do that partition pruning and just get the data for that specific tenant. And then all the way on the right here, as I said, you unlock this huge ecosystem of tools that allow you to utilize your data in Iceberg. So on the open source side, you have a ton of options. Only a few of them I added here. You have Spark, Trino, Flink, StarRocks, Hive, DAF, as well as many, many more. On the SDK side, Iceberg offers Java, Python, as well as Rust SDKs. So, really kind of a growing ecosystem there in terms of if you want to roll your own, if you want to create your own utilities, create your own, tools that connect into Iceberg, you have really good support there. As well, there's a ton of managed compute options as well. A lot of the major cloud providers have really taken up Iceberg, as well as a ton of other, tools as well. So you have things like AWS Athena, GCP BigQuery, which I believe there was a talk actually just before mine about BigQuery and Iceberg support, Snowflake, Seller Data, which is managed StarRocks, Dremio, obviously one of the sponsors of the conference today, and then Starburst Galaxy as well. And there's tons of others here that I wasn't able to mention either. So at this point, we have our data consistently replicated downstream into our Iceberg tables. We have a huge set of options of tools that we can use for our data stack. So what's the data stack that we picked? So this is what we refer to as our unified data platform. So the idea of the unified data platform was that we would have a centralized data platform where we would store all of our data at DemandBase. So that is not to say that we're not going to have other data stores and other tertiary tools here. We of course will. Iceberg is not going to solve all of our use cases. But the goal is that, especially for any data sets that are used across teams or across products, the source of truth for that data should be the unified data platform. And the core of that unified data platform is all data needs to be stored in Apache Iceberg tables. Because the number one thing that gives us is interoperability. If all of our data internally is in Iceberg format, any team that has a way of accessing this unified data platform, whether that be Spark or something else, can access any of the data in our unified data platform. In addition to that, because we're using Iceberg, we have found this to obviously be a very scalable, very performant, and very cost-effective way of storing our data and utilizing it for a whole variety of use cases. Like I said, analytics, data science, et cetera. So the tools that we have picked are obviously storage, Iceberg tables on S3. For our catalog, we were using the Dynamo catalog as well as the Glue catalog in some places. We have since started and completed actually a lot of our migration to the REST catalog that is managed by Tabular. For batch and stream processing, we utilize Spark, specifically run through AWS EMR. For many of our teams internally that are not data engineering teams, they really need a direct SQL interface. So this is a lot of our application teams as well as our non-engineering teams like customer success, technical support, etc. So for that, we use AWS Athena. As I said, Iceberg is never going to solve all of your use cases. One of those being really low latency analytics queries. So for that, we're utilizing StarRocks, the managed version via Seller Data. And then one of kind of the final problems here that we found is because we have essentially what ends up being a data mesh, because we store our Iceberg tables in a variety of AWS accounts and a variety of S3 buckets, you have that gives you a lot of flexibility in how your teams utilize the data and how they store their data and organize it, but it makes it very disparate. How do you have kind of a clear view of what all data you have and how to use it? So this is where our data catalog comes in, and we're utilizing Data Hub, specifically the managed service through Acro Data for that. And this really gives us a really nice way of documenting all of our data sets, how to utilize them, sample queries, profiling, et cetera, so that teams can have a place to go and see all of the data that's in our unified data platform, all of the sources that feed data into our unified data platform, and get information on how to utilize it. So the nicest thing here for us has been that these tools all work together really, really seamlessly. So one of the things that was really hard for us, maybe 3 or 4 months ago, was cross-account access. So as I said, we have a number of AWS accounts, and we're actually moving to even more of a multi-AWS account structure, as well as a number of S3 buckets. When utilizing the Glue catalog for our Iceberg tables, we found that cross-account access was quite an arduous process. We had to go through AWS Lake Formation permissions, which worked very well, but the setup and the management of it took a lot of time and a lot of understanding of how those things worked and how to get them to work together. However, since migrating to Tabular, because you have this separate catalog that does the authorization for you and does all of that access management, you're able to really seamlessly give access to users, give access to IAM roles in Tabular, and then they're able to make that call and get access to the data that they need. So it makes the cross-account access so much easier. Additionally, with Tabular, because you can not only give access to users and tokens, but you can give access to IAM roles and assumed roles and et cetera, you're able to directly authenticate with IAM from AWS EMR or Athena, and you don't need to do additional setup. You don't need to provide tokens to users. You don't need to worry about secret management inside of your pipelines. You're able to directly authenticate using your IAM roles very similarly to how you would with the Glue catalog or the Dynamo catalog, in that you don't need additional credentials. You just need that role. And then, a number of these other tools as well. Spark obviously has great support for Iceberg. One of the big ones for us as well was how do we get our data into our OLAP database? Previously, we were using databases where to do this, we had to actually go to Iceberg, ask it what Parquet files are part of the most recent snapshot, and then give those Parquet files to the OLAP database to load because it didn't have an integration into Iceberg. However, now by using StarRocks, because you can natively query Iceberg tables directly from StarRocks, we no longer have to do that. We can simply run insert into select, where we're inserting into an internal StarRocks table and selecting from an Iceberg table, and we can load our data much more easily by doing this direct integration and doing this direct querying out of our Iceberg tables. So we've gotten a ton out of this by these tools really seamlessly working together and having this big ecosystem for us to pick from, such that we were able to find tools that really were able to fit our needs and not be limited by what supported Iceberg. In addition to this, we've of course built a number of things internally. So all of our Iceberg maintenance, we run and orchestrate ourselves. We've built some catalog provisioning via Terraform, where we can spin up catalogs as well as the necessary resources like S3 buckets and IAM roles and Athena data sources, all with minimal configuration via Terraform. And of course, as I talked about extensively, we built our own change data capture into Iceberg, which some vendors now have managed versions of as well. So we were a little ahead of our time there and built that ourselves. So with all of that, that is how DemandBase built our unified data platform. So really quickly, one plug, we're hiring. So if you're interested in joining the team that built the data platform that I just talked about, please reach out, please apply. So we're hiring for a senior data platform. I listed some of kind of the high level tools and technologies that we utilize on the team. So we would, if you're interested, if you're here today, you are very likely quite qualified. So please apply and reach out, and we'd love to hear from you all. With that, that is it. Thank you all for the time, and really appreciate it.
Great. Thank you so much for that, Ryan. Now I would like to go ahead and open it up to questions from our audience. You can go ahead and type them in on the Q&A tab, or if you would like to go request to come on camera, you may also do that as well. So we have a handful of questions. Ryan, I'm going to go ahead and start from the bottom here. How did you get the old, is it DAT or DAT out of RDS?
Yeah, so I think that was supposed to be data. So what we ended up doing is RDS has the ability to do to take a snapshot of your data and then export it into S3. So it works very well because it doesn't have a large effect on the performance of the RDS instance, which, as I said, was a big thing for us. However, it is very, very slow, and it is quite costly from AWS. So this really for us is just an initial method that we utilize when getting the initial data out of our RDS instances, as well. It's kind of a backup recovery process. So if we do have any issues with our CDC process, we are able to recover in that way by pulling out those snapshots. But that's really kind of a last case scenario. When we're spinning up new databases now, blank from scratch, we ensure that we get CDC started right away, so that the second there are changes from customers on those databases, they're flowing into our CDC process.
Okay, perfect. Moving on to the next one. How did you manage to mimic in Iceberg tables the table level key constraints, which are present in Postgres?
Yeah, absolutely. So we don't really, honestly. So we don't have key constraints on our Iceberg tables. So things that do have foreign keys in Postgres don't have something similar currently in Iceberg. That is somewhat by design. CDC as a process is inherently eventually consistent. So to some extent, that is by design, that reconciliation for one table might happen before another table. So knowing that and kind of intentionally saying that we're not going to deal with that complexity in terms of reconciling data based on the ordering and the cascading ordering of those keys, we've cut down all of that complexity and just inherently know internally that CDC is a eventually consistent process that doesn't have those specific constraints.
Okay. How often do you refresh tables with minimal changes?
Yeah, absolutely. So it kind of depends on the type of table. So they kind of fall into two buckets. One being really easy tables. So these are your typical RDBMS tables where it's, I don't know, maybe 10 or 20 columns, and they're all, simple values. They're ints, short strings, longs, whatever it may be. These tables are, even for a high volume of changes, are very easy and very quick to reconcile into Iceberg. The merge happens, relatively quickly. So we're able to do it on a relatively low cadence. So we've really kind of traded off cost and performance, particularly of the reconciliation process, with our refresh kind of latency. So with that, for those easy tables, we do it every hour. But we're able to, if we wanted to, pay a little bit extra cost in terms of the cluster and resources. We've gotten that latency down to a few minutes. And then for our kind of harder tables, which are really the toast tables, those ones we do on a daily cadence. And this is really because doing that merge can be relatively difficult for kind of two primary reasons. One, these rows can be very, very large. Like I said, toast values can be hundreds of kilobytes or even megabytes, and a row can have multiple of those toast values in it. So just writing that data out can become, relatively slow because of those large data, the large amount of data in those rows. Additionally, because of the nature of the data, it's relatively difficult for us to organize the table in such a way that we can do the merge efficiently. So one of the primary axes for optimization when you're talking about merge into is how much data you get out of your target table. So really, really making sure you minimize the set of data that you're joining to your source table. And for a variety of reasons, because of the way these tables are structured and the data that they contain, doing that optimization to minimize that set of data becomes relatively difficult, and we have to pull out a lot of data kind of all of the time. So for those tables, it becomes relatively hard, and therefore, because of our internal requirements around cost of reconciliation, et cetera, we do those on a daily basis.
Okay, great. Next question we have is, why did you choose Data Hub for catalog instead of Glue catalog via AWS?
Yeah, absolutely. So we had always known that we were going to move away from Glue as our Iceberg catalog, right? So we were on Dynamo. We used Glue some as well. We always knew that we wanted to move toward the REST catalog. So in that case, because we don't have, because we know we're not going to use AWS Glue necessarily, we wanted our data catalog to be somewhere else, to be somewhere more centralized. Additionally, because we have right now, I think we have 7 or 8 AWS accounts that have Iceberg tables in them. And we're, like I said, we're pushing toward even more. It's very difficult to have kind of a centralized Glue catalog across all of those AWS accounts. So you have to do, a variety of things in terms of lake formation and Glue catalog sharing, et cetera. So we kind of, from the jump here said we really need to have a separate, agnostic of AWS, and agnostic of a lot of our platform catalog that can ingest data from all of our different sources. So this isn't just Iceberg, it's all of our upstream and downstream sources as well, like StarRocks, like BigQuery, et cetera.
Okay. Two-part question. Where do you store Iceberg metadata? And the follow-up to that is, how do you back up and restore Iceberg tables?
Yeah, absolutely. So our Iceberg metadata, the metadata files themselves are stored on S3 as well as the data. And then we used the REST catalog, specifically Tabular's REST catalog for our Iceberg catalog. In terms of backup and restorative tables, so we do a daily job for some of our tables where we snapshot them into a logically separate namespace and table inside of our Iceberg tables. We have looked at using Iceberg's internal CDC out of Iceberg into another Iceberg table. We haven't gotten there yet, so we're doing kind of a bulk extract of data. For the most part, we do this just for the tables where that are most sensitive and that we don't have an upstream, particularly in Postgres, that we can recover from. Because there are some tables where teams are writing directly into Kafka for us, writing change messages. So for those ones where we don't really have a source of recovery, we do that snapshot.
Okay. We've got roughly probably 1 or 2 more here. Let's see. Is StarRocks comparable to Trino?
Not quite. I think there is some overlap there, especially in terms of StarRocks's what they call it, a shared data cluster format where there's kind of no persistent disk. However, kind of a general use of StarRocks is more so like a general purpose OLAP database, like a ClickHouse or something like that. Is kind of more where StarRocks overlaps with other tools.
Okay. Do you run any maintenance for Iceberg tables? Also, do you have any retention policy?
Yeah, absolutely. Yeah, so we orchestrate all of our own maintenance through Airflow DAGs. So we utilize the Spark procedures to do the maintenance. So we do all of your typical ones. We do snapshot expiration, we do compaction, we do orphan files, all of those typical Iceberg maintenance processes. We do have a retention policy, so we keep a certain number of snapshots as well, because of the nature of our data, nature of a lot of our data being by customer. We also have a separate custom Iceberg maintenance process that looks at our customers internally and says if a customer has churned within the last certain period of time, we only retain their data in our data platform for a certain period of time, and then we kind of manually delete the data for that customer. So we have that kind of custom Iceberg maintenance as well.
Okay. Let's see if we can get last one in here. All right, I think we kind of went through all of them. I'm going to try to see if I can bring this person on board here to answer a question. Oh, no, it went away. Okay.
Mhm.
All right. So let me go put this back up here. All right. So, well, once again, thank you guys all for joining us. Once again, Ryan, thank you so much for this as well.